Okay, so now we want to talk about the chain rule again, but now we're talking about where we have a multivariate function like we've been discussing. So remember the chain rule before, we had something like this. We had h, which was actually f circle g of x. In other words, we're putting a function g into a function f. And then we had the chain rule, which we said one way to write it was like this, but this is sort of more typical, and we write it like this. So this says that we have y is actually the h, so y is the final output. So y depends on g, what we put into g, which is usually called u. So we have y depends on g, or u. U is just another name for g here. And then u, or g, depends on x. So the chain rule says that to get the change of this thing, which we're calling y, with respect to a change in the inner variable x, we do the change in this thing, which we're calling y, with respect to a change in g, or u, and then the change in g, or u, with respect to the innermost variable x. So that is the chain rule. Now, we didn't go over this too carefully because it's expected that you've studied that before. So we're using kind of standard notation here with u and y, but we didn't really explain all of that when we presented it earlier. So here I have a slightly different way of writing it, but instead of g, I'm calling it x. So we have h is actually f of x of t. So the inner function here is called x. So we see that h depends on x, but x depends on t. Okay, that's the original version. But now we're doing h depends on two variables, and we're going to give the notation for the two variables as a vector. So we're saying that h, or f, depends on this vector, which we can write explicitly like this. So f depends on two things, x and y, but each of those depends on a single variable t. So the picture looks like this. So you have h depends on a vector. In other words, it depends on two things, whereas here h only depended on one thing. So we have not a bold x here, but we have a bold x here to indicate that h depends on two things, or a vector. And then that vector, this bold x, is equal to this vector. So it has two components, x and t. So this is a kind of confusing notation because we have bold x, and then when we write it in components, we write the first component as x, which is admittedly confusing. That's the kind of standard way to present this, but actually I find it unfortunate notation. But anyway, that's the kind of standard way, so I'll stick with that and say that f depends on two things, which we denote as a vector, and we kind of naturally call it x because naturally, typically, we say that f depends on some x, but here, as I said, it's a vector. It's two things. It's not just one. So, and the two things are one thing, another. Now, again, it's unfortunate that the one thing is also called x, y. But again, that's pretty standard, right, to put x, y. So that's why we kind of run into this confusing notation. So anyway, this is x, y. And then each of those x and y both depend on one additional variable, t. So we have h is a function of x, where x has two components, like this, but each of those components is a function of the single variable t. So, of course, we can say that h changes as x changes. But if we're going to write that in some kind of calculus notation, we'd better use the curly derivative sign, or in other words, the partial derivative sign. So, of course, h depends on both x and y. So if we're going to take the derivative of h with respect to either x or y, we have to use the partial symbols because h depends on both x and y. However, we also know that x depends on t and y also depends on t. So this small x depends, or non-bold x depends on t, and this non-bold y also depend on t. So, of course, if we change t, this x will change, and of course, if we change y, this y will change. But do we use the curly symbol here, or the regular d, the full derivative? Here, we're going to use the full derivative because x only depends on one thing. So we don't use partials in that case. So we would write, so if we're going to talk about the derivative of x with respect to t, we shouldn't use the curly symbol for partial derivatives here or here. So in our original consideration, when we were talking about the chain rule, we were talking about a function f of a second function, we called it g before, but here we're calling it x, of t. Now we're talking about a function f of two variables, but then each of those variables depends on just one variable. Now we could also consider where each of these variables depend on more than one inner variable, but we're not going to talk about that right now. We could talk about it. We would talk about that next if we were going to talk about it, but right now we're only going to talk about x depending on one variable, y depending on that same variable. So this is the scenario. This picture is what we're currently considering. We also could, as I said, consider that x depends on t and maybe some other variable s, and y also depends on t and some other variable s. But right now we're going to leave that alone. So here's that situation in the text. So we have that f is a function of two variables, and g, the inner function, which we just called x, or we also call it x here, but the inner function is a function of two variables. So this bold x is a function of two things, x and y. And then I point out in the text that this is admittedly confusing since one of its components of the vector x is also called x. So, okay, with this scenario, let's take an example. So let's say that we have the outer variable is called z here, and it's clearly a function of two variables. So we could say it's a function of a vector. And the way that it depends on these two is it's 2 times the first variable plus the second variable squared. Okay, so that is this situation. So we have we called it h here, but maybe I should rename it z. So z here, z is a function of x and y. That's what we have here. So this is a function of this vector, which is really x and y. Now notice here that the situation is that this is not a bold z, this is not a bold h. That means we don't get a vector out. Remember we talked about getting vectors out versus not getting a vector out. So we're not getting a vector out here, so we're just getting a number, a single number or a scalar, and that's what we get here, right? If we put x and y in, but we're only getting out a single value here, right? Suppose x is equal to 1 and y is equal to 1. What do we get out? We get 2 times 1 plus 1 squared, so that's 2 plus 1. We get 3. We get the number 3 out. So that's the scenario we're considering here. Now we also have to explain how x and y both depend on some variable t. So let's check that in the text. So remember, x and y can be written as a bold x, and then we're suggesting that it depends on t, and that means that the bold x means there are two components, so we have to explain how each component depends on t, and here we do that. So in this example, the way that x depends on t is it's equal to 6t, that is not the bold x, but this x, and the way that y depends on t is t plus 2. So in our picture, we would be saying that x is the function 6t. That is, here we would say this function is 6t, and then y, I think, was the function t plus 2. Yeah, y was the function t plus 2, so we want to put that in the picture as well. So we get that. So we have z is a function of a vector. In other words, it's a function of two components. It's a function of x and y, and this is in our example in the text, this is the way we're going to do it for z or for f. And then x is a function of t. We have to give an example for that. So we give an example. We say, suppose x is 6t and y is equal to this. Okay, so now what are we trying to ask? So is this what we're trying to figure out? Is this what we're trying to figure out? No. Is this what we're trying to figure out? No. Is this what we're trying to figure out? Actually, we're going to need to know all of these pieces, but that's not the original question we want to ask. So what is the original question we want to ask? We want to know, how does this, or h, we can call it z or h, how does this change, not when x and y change, we will need to know that, but what we're trying to ask here is, how does this depend on the change in t? So how do we write that? For our chain rule example, we want to write, I'll write it in green, and I'll make it a little bit bigger just to emphasize that that's what we're looking for. So it's d z d t. So this is what we're looking for. We want to know, how does z change with a change in t? Now, from the picture, you can see, or you might recognize it anyway, that when t changes in the sort of intermediate level, that's going to cause a change in x, and it's also going to cause a change in y. And then those changes in x and y are going to cause a change in z. So we have a kind of chain rule effect, or a chain effect. So what is the actual formula that's going to give us this answer? What's the formula that's going to give us this? Whoops. What's the formula that's going to give us this answer? So let's take a look at it. Now remember what the simpler question was, when we were only doing where there was only one intermediate variable, just x, or actually we call it u here, sorry. We call it u here, but there was only one intermediate variable. In other words, in this picture, this situation where there's only one intermediate variable, x. So if we recall the chain rule in this case, I'll write it here. But before I do that, let me also call this z for this example. So z is that, and then the chain rule in this case for this simpler example, where there weren't two intermediate variables, was what? Let's recall that. So this was the original answer. This was the chain rule, the original chain rule. Now what we're going to get, though, well, first of all, in the book, this is what it looked like. So instead of instead of t here, I'm using x. So dy dx is dy du. That's the intermediate variable in the book, and then du dx, okay, which is like this. dz dt is dz dx dx dt. So this says that if we want to know how z changes with respect to a change in t, we ask, how does z change with a change in x, and then how does x change with a change in t? But now in the more complicated situation, we see that z, when we change x, then x is going to depend on the x is actually two things, it's x and y, small x and small y. So it's going, and they are each going to depend on t. So the expression should be more complicated. So we might expect it to look something like this. So we have dz dt, dz dx, dx dt, and then somehow else we have to have dz dy, dy dt. But there's something wrong with this besides the fact that I don't have any bars here or plus signs or equal signs. But besides that, there's something else that's wrong here. So what else is wrong here? Well, this symbol is wrong here. Why? Because we said that z depends on both x and y. So we shouldn't use this symbol for the derivative in that case. And the same thing here. When I write z, this would suggest that z only depends on y. This would suggest that z only depends on x. But both of those are not right. So I should not use these two symbols. So I have to handwrite those other symbols. So I'll do that. So this is the way it actually looks. And notice that here we have a partial and here we have a partial. They should not be full d's because z does not just depend on x, it also depends on y. So we have to use the partial here, but at the level of x, x only depends on one variable. So we do use the full d here. This is the full derivative. And we do use the full d here. This is the full derivative. So this is what the new chain rule looks like. Now it looks almost exactly, the first part looks almost exactly like this. dz dx dx dt, dz dx dx dt. The difference though here is we use partial, and then but the full doesn't just have this term, it also has this term. So this is the chain rule for this scenario. Now let's take a look at the example that we did in the book, which is actually this example here, where z depends on x and y, and then x and y both depend on t. Now you can see that there might be another way to do this besides doing it this way, because if z depends on x and y, and if x and y depend on t, then we could just take whatever x is here, and replace it by 6t, and whatever y is, replace that by t plus 2, and then we're just going to get an expression for t, and then if we want dz dt, we can do it very simply. We don't even need the chain rule. So let's see how we do that in the text. So it's called Example of Multivariate Chain Rule in the text. And here we have z is a function of x and y, and this is the function of x and y for our example. And then x, the vector x, has two components, and each component is a function of t. So that's the example that we're going to do here. So now we want to know, when we change t, how does z change? That is, we want to know, here's the way it's written in the book, and here's the picture. And if we're going to use that in this example, we would want to know the first term is the partial of f with respect to x times the full of x with respect to t. So we need the partial of f with respect to x. So that's here. And the partial of that, remember, if you take the partial of this with respect to x, then this is a constant. So the answer for that is just 2. So this first factor here is 2. And then we also need dx dt. Now, here's x. So how does x depend on t? It's 6t. So we want the derivative of that with respect to t, and that's just 6. So that's this part, or that's this part. And then we need this part. So we need the partial of f with respect to y, not with respect to x. And then the partial of y, not x, with respect to t, So we want to do that. So the partial of f with respect to y. So now we want the derivative of this with respect to y. So this is a constant. And so we get 2y here, so that's 2y. And then we want the partial of y with respect to t. That's the derivative. Here's y. So here, t plus 2, the derivative of that is just 1. So we get the two factors here are 2y and 1. So we get 2y here. So the final answer, according to the chain rule, is 2 times 6 plus 2y times 1. Now, if we want to put this all, we can put this all in terms of t, because what is y? We can rewrite y as t plus 2. So we could write that, we could leave it like this, but we could also write 2 times 6, which is 12, plus 2 times t plus 2. So if we do that, we end up with this. 12 plus that, which is 16 plus 2t. So that's the answer if we use the chain rule. But we said there was another way to do this as well, because we can just take, here's the f as a function of x and y, and then we can just say, well, x is 6t and y is t plus 2. So we just put those 6t in here and t plus 2 in here, and then we're going to get an expression with just t's in it, and then we can just take the derivative with respect to t. Now, hopefully, if this chain rule that we came up with is right, then when we got this answer, we should still get the same answer if we do it with this sort of substitution. So we do that actually above. So let's see that. So here's the same f, and then we replace x by 6t, replace y by t plus 2, so we get this, and then we can simplify that to this, and now we want to know the derivative of this with respect to t. Notice that this is not a partial derivative, right, because f at this level only depends on one variable, t. We weren't talking, that is here, z at this level only depends on one variable, t. As I said, we could consider a more complicated situation where it depends at this level on more than one thing, and that would be something we would like to do eventually. But right now we're just considering where it just depends on one variable at this level. So we don't write partial of z with respect to t, we write full derivative of z with respect to t. So anyway, going back to our example, we want this, and we have this as our expression now in terms of t. And so if we take the derivative of this with respect to t, we get 16 plus 2t, and hopefully that's what we got down here. 16 plus 2t. So we got the same thing. So that it gives us some confidence that our chain rule is working the way it should be. Okay, now the next thing is that the intermediate variable x, which is actually a vector, so it's not just one variable, it's this one and this one, but we could generalize to say that this is not just a function of just x and y, but how about if it's a function of many variables at this level? So in other words, we don't just have x, y, we might have another variable here and another variable here and another variable here. And we might like to come up with a chain rule for that scenario or that situation. Now, instead of calling it x and y in that case, it's probably more convenient to call it x1, and it depends on x2, and it depends on x3, and we might have any number of variables at this level. So we'll call them x1, x2, x3, and we'll say, let's suppose it goes all the way out to xn. And then what would the chain rule look like for that? So again, we didn't prove this rule, and we're not going to prove this rule, but we could. And if you go to the book that I recommended by Coley, you can see the proofs, or you can see it in many other texts as well. So we want to consider the situation where the intermediate vector or intermediate level is a function of many variables. So what's the chain rule going to look like then? So whereas before it was only 2, and then we had 2 components, or 2 terms rather, now we're going to have n terms. So the first one is going to be the partial of z, or the partial of f, with respect to x1, and then that x1 is going to depend on t, so the partial of that with respect to t, and then the partial of this with respect to x2, and then that x2 is going to depend on t, and we're going to just continue out to the last variable, the partial of f with respect to xn, and then that xn is dependent on t. That's this picture here, where we have many variables here, x1, x2, x3, x so on, but each of them is dependent on t. So again, let's check to see where we have the curly t, or the curly d, or the soft d, versus the hard d, or the full derivative. So where does that occur? So here we have the soft d, the partial d. Here we have the partial, here we have the partial, but here we have the full derivative, here we have the full derivative. So is that right? Yeah, because at the beginning level, the function depends on x1, it depends on x2, it depends on xn. So those should all be partials. And then, but at the final level, each of those, x1, x2, and so on, depend only on one variable in the case that we're talking about. This depends only on one variable t. This depends on the same variable t. So we can confirm that we should be getting partials here, but full derivatives here. So this is a more general chain rule where we can have the intermediate variable, which we've called a vector x, has many components, n components. Okay. Now, this is kind of magic. What did the chain rule say? How about when it was just x1 and x2? So if we had f, can anybody kind of bring it back up without going back and looking at it? I had x and y, but I'm going to call it x1 and x2. Can anybody kind of recall what it was? There were two pieces. They were both, I put green boxes around both of them. So there was one green box here and another green box here. Does anybody remember what they are? Okay, what was it? D, F, no, partial, sorry. Partial, F, partial, X, and then, oh, sorry, X1, sorry, right. X1, then it was D, X1, D, T, right? Okay, then, oh, sorry, that's not supposed to be there. DT, okay, good, excellent. So, I can't erase that. Can't erase that. All right, anyway, that's not supposed to be there. Can't erase it. Okay, so, and then what about the second term?
Partial of df.
All right, partial f.
By partial x2.
Good. You know, look at this. You guys can even do this because you understand, you know, when it should be partial and when it shouldn't. So you can actually, like, I couldn't even remember this, but you're able to do it. Okay, so what is it? D?
x2.
X2?
By dt.
Dt. Okay, good. Now, watch this. So if we wanted to, okay, so watch this. Let's define a matrix. Watch this. I'm going to define a matrix. Let me put it over here. Matrix, a one-dimensional matrix, or, yeah, a one-dimensional matrix. I'm sorry, not a one-dimensional. A row matrix. Okay, let me define a row matrix. So, and I'm going to have a row matrix with just two pieces. Now, usually we don't put commas in a matrix. In vectors, we put the commas, I think, but in matrices, we usually don't include commas. So I'm not going to put any commas here, but I'm only going to have one row, and it's only going to have two elements. Okay, now let me do this. Watch this. I'm going to have this element going to be partial of f with respect to partial x1. And then I'm going to have a second element, and that's going to be partial of f with respect to with respect to x2. This is going to be x1, right? Okay, do you let me do that? Okay, now let me make a second matrix. And this one is going to be a column matrix. Okay, let me do this. You can't stop me, right? I can do this if I want. And what I'm going to do is I'm going to put in here two elements. This is also going to have two elements. D x1, that's supposed to be D. And this is supposed to be D. T. Oh, sorry, that didn't work. I wrote that wrong. Wrote it too big. Okay. All right. Let me try that again. So this is D. That's supposed to be a D. X1 dt. And then the bottom one is going to be D x2 dt. So sorry about this not being very clear. Do you understand there are two pieces in here and there are two pieces in here? Now, here's the magic. If I take this matrix times this matrix, so this matrix is what are the dimensions of this matrix? 1 by 2, right? And what are the dimensions of this matrix?
2 into
2 by 1, right? So are we allowed to multiply these two matrices? They have the right dimensions? Yes. And the resulting size is going to be what? 1 by 1, right? And what are you going to get when you multiply these two? So you're going to multiply this times this, right? And you're going to multiply this times this. And then you're going to add them, right? And what do you get when you do that? You get that. So we can say that oh, by the way, this was supposed to be the derivative with respect to t, right? I forgot to write that, right? The derivative with respect to t, right? So the derivative of t, the derivative with respect to t using the chain rule for this much more complicated situation where we have two input variables, and then each of those are dependent on just one t, right? They're both dependent on t. So in this much more complicated scenario, we got this answer. Now we can express it like this. We can say, call this one A, or what should we call this? I don't know, whatever I'm going to call it, call it something. I think there's a better name than A. And call this B. The answer is just going to be 8B, where this is A and this is B. So the whole formula is right here, just AB. We can express it so nicely as A, where A is this kind of matrix, and B, where B is this kind of matrix, and that's the whole thing. And now, if we have many more variables at this level, then it's going to look like this. This is going to be A, and this is going to be B, and we just multiply them together, and that's still going to give us the chain rule. So we have this very elegant expression of the chain rule as just a particular matrix this kind times this matrix here. And that is the chain rule. Okay? So that's quite nice. as an expression of the chain rule. And you guys sort of probably can now generate in your own head. Whoops, it's time to stop, right? Okay. But you guys you already did it once. You generated what should be in here, or actually what should be here and here. And you also generated what should be in here. That is what should be here and what should be here. So you can basically do this in your head. And now we can say that the chain rule can be expressed as a matrix product, right? Which is quite nice, right? The whole chain rule, this very complicated mess, is just going to be the product of two matrices, right? So that's a nice result. All right, we have to stop now. So we'll come back next time. All right, but for homework, you should finish chapter 10. Okay, and if you didn't finish, if there's anything left in chapter 9 that you didn't do, you should do that as well. So we covered probably most of what you need. So here, remember, we talked about the gradient. Here it is. Here's the gradient, right? We said that. That's the gradient. And there it is. And here, well, anyway. Okay, yeah, and that's the end. So we covered basically everything. So now, so you should be able to do this chapter. Okay, and then next chapter, we finally get to doing neural networks. So we're going to cover these things. And then the neural networks, the way they learn is using this gradient descent. That's how they do all their magic. That's how they learn. So that's why we needed the gradient descent. And that's why we needed the partial derivatives, because the gradient descent is about derivatives. And now we know the chain rule for derivatives, right? Do you understand? Gradient descent is about derivatives, right? We certainly established that, right? Because you want to talk about how high you have to, you need to walk in what direction. So we need that. So gradient descent is certainly about derivatives. And now we've talked about derivatives in a very powerful way, multivariable derivatives. And we call them gradients and whatever. But and we have the chain rule for multivariate derivatives. And we even express that as just a simple vector equation. I'm sorry, a simple matrix equation, right? So we have that very powerful chain rule, which is certainly about derivatives. And so that means it's going to apply to gradient descent. And we have it in a very simple way, expressed as a very nice way, as a matrix multiplication. And now we are going, and this gradient descent is how neural networks do their magic. And they certainly do a lot of magic these days. Like that whole tool that I used there today at the very beginning, that math picks thing, that was using image recognition. That's great. That's neural network. That's gradient descent. That was using gradient descent to figure out, what symbol did I capture, right? Okay, so the whole thing is based on this gradient descent. Okay, that's all for today.